Keep talking, boy, keep talking. You get momentum where P is equal to mv. I love equations, oh, I love equations. Another thing to know is momentum is conserved in every situation. Collision momentum, go, 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 go. Shut to the heart, and you're too late, darling. You give love a bad name.
What you see here are the formulas for conservation of energy and conservation of momentum. Energy's units are joules, while momentum is kilograms times meters per second. The first formula for energy, mechanical energy, equals kinetic energy plus potential energy, because the energy must remain constant throughout the transfer or whatever. It's the conservation. The bottom equation reads 1/2 mass times initial velocity squared plus mass times gravity, which would be 9.8 meters per second, times the initial height equals 1/2 mass times the final velocity squared plus the mass times gravity times the height. Momentum is equal to mass times velocity, and it too must remain constant, so the initial momentum will equal the final momentum. Okay, so we have Unit 3, which is conservation of, what was it, energy and momentum? Yeah, so here's our problem. So first we need to find the speed, and we can use, since we know formula m1v1 plus m2v2 equals m1 plus m2, and I should probably put that in parentheses, v prime. Okay, so here is the mass of the bullet, which is m1. Right here is our initial velocity, so v1. Let's see, the block of mass would be m2. And it's at rest, so that means v2 equals 0. Equals m1 again, 0.01 plus 1 v. Okay, so this we know becomes 0. This we can go ahead and simplify to 1.01. So grab a calculator because, you know, I hate math. So we're going to do that from 1 times 200, which equals 2, which I probably should have been able to do in my head, equals 1.01 v. So you're going to divide that by 1.01, and you get v equals 1.98 meters per second. Alright, now for the change in kinetic energy, kinetic energy equals 1/2 mv squared. Alright, so to find the change in it, we're going to do kinetic energy equals Ke final minus Ke initial. So that's going to mean 1/2. Alright, so we had 1.01 for the mass, and our velocity from the last problem, which was 1.98 squared, minus 1/2. That'd be the 0.01 because it was our initial. And our initial velocity, which was 200 squared. Yay, more math. So 1.98 squared times 1.01 times 0.5. So that equals 1.9798 minus 200 squared times 0.01 times 0.5 minus 200. So, let's see, because I am lazy, just go back up here, minus 200. So we get the change in kinetic energy. Should probably put my little delta for change. Kinetic energy equals negative 198.02 joules. Alright, next we have to find the distance. So we have the y and the x. So what do we know about the y? We know that the initial velocity is 0. We know that the acceleration is -10 because 9.8 gravity and it's falling. And we know that the distance is -1 because it is falling 1 meter, where it says, well, it says somewhere, height of 1 meter above the floor. So we need to find time. And to do so, we use D equals V1t plus 1/2 AT squared. So that'd be -1 equals 0t plus 1/2 -10t squared. This we can go ahead and cancel to 0. So divide by 1/2, that'd be, so that'd be -2 equals -10t squared. And because I'm lazy, got 0.2 equals t squared. So we're going to square root 0.2. We're going to get, okay, I'm just going to round that, it's a big number, but we're going to get t equals 0.45 seconds. Alright, next we have to find everything we can about the x in order to find the distance right here along the x-axis. So we know that t is 0.45. Our v is from part A, which was 1.98. We have no acceleration because the acceleration is constant going across the x. And we are trying to find the d. So we're going to use that same equation from before, the dVt 1/2 AT squared. This time we're going to put in 1.98 and the 0.45 will be plus 1/2 0.45 squared, and that's just going to go ahead and be a 0. Then 1.98 times 0.45. Alright, so D equals 0.891 meters. So yay. Speed of the bullet when it hits the ground Okay, another magical angle change. Alright, so speed of the bullet when it hits the ground. So we're going to use one of our conservation of energy equations. So that'll be 1/2 mv squared plus mgh equals 1/2 mv squared. Okay, so, jeez, I'm gonna die. Okay, so 1/2 the mass, which was 1.01, and then the velocity, which was 1.98 squared, plus 1.01 times, I'm going to go ahead and use 10, just keeping it consistent, times 1, because that's how high the table is. And it has to equal 1/2 mass times the velocity squared. Okay, so these are the same on both sides, so we can just go ahead and cancel them out. And this one too. Then we have, so that's 1.98 squared times 1/2. So that's 1.9602 plus 10 equals 1/2 v squared. So we're just going to go ahead and add 10 and then divide by 2, because that's actually divide by 0.5, sorry. Okay, so after dividing by 1/2, you get 23.9204, which I'm not going to write due to room, but then you would square root that, and you get v equals 4.89 meters per second. Alright. And then suppose that the bullet is accelerating to its initial speed by a spring that is compressed 0.1 meters. Yay, spring. Okay, so our spring equation is 1/2 k.
Let them in these thoughts of sleep. Be the good girl your parents want you to